So we are going to review a couple kinetics problems with regards to the AP Chemistry curriculum. We have a selection across the curriculum for this particular topic. So we'll start with just a simple gas law question. It says, consider the gas phase reaction between nitric acid and bromine at 273 degrees Celsius. The following data for the initial rate of appearance of Nobr were obtained. A. Determine the rate law. So, determining the rate law, let's get the table in the picture as well, is a pretty basic request. There's really two things you're really looking for. First of all, we have 4 different sets of experiments where the concentrations were varied. You're looking for experiments where one variable was held the same. So experiments 1 and 3, the nitrogen monoxide was held constant. In experiment 1 and 2, bromine was held constant. Our job is to basically see what those changes do to the rate. So the general rate law that we would normally look at is rate equals K times the concentration of NO to the X, the concentration of bromine to the Y. It's the general form. So the goal is to figure out what X and Y were. So to do that, I'm going to start with identifying what bromine was. So I'm going to use experiment 1 and 3 for that because nitrogen monoxide was held constant. So for no particular reason, I'm going to write rate 3 first, just because I believe that when I divide rate 3 by rate 1, I will get a number greater than 1, and I find that a little easier to deal with. So rate 3 is equal to the rate constant times the concentration of nitrogen monoxide to the X for experiment 3. So that subscript just is referring to the experiment. We can put it in a circle just so we remember that that's not anything other than that. And bromine, that's also for experiment 3. And we're going to divide this all by the rate for 1. Now, while we do this, it can be very straightforward when you look at the data from the experiments. You might not need to do this. You might be able just to say, if I doubled one reactant, the reaction doubled as well. This is really the in-depth way to do it if you're going to end up with odd numbers. So now we just fill things in. So the rate for rate 3, the rate for rate 1 is equal to K. The concentration for rate 3 is 0.1 molar to the X, 0.50 molar to the Y, and experiment 1 is 0.1 molar to the X and 0.20 molar to the Y. Now, this part is all going to just cancel out, and that allows us to sort of simplify what we're doing. So first up, let's go 60 divided by 24. Hit that right. It's 2.5. The units will also cancel. Is equal to 0.5 divided by 0.2. So we have 2.5 is equal to 2.5 to the Y. So I think it's pretty clear that Y must be equal to 1. We will do this, we have to repeat this one more time because we've solved for Y. You can substitute in data, but we don't have the K, so we might as well just do this again. But instead of using experiment 1 and 3, we're going to use experiment 1 and 2. So rate 2 is equal to K times X BR2 to the Y. This is experiment 2 over rate 1 equals K NO to the 1 . Now I have solved Y. I know that Y is equal to 1, so we could probably just substitute that in. It's not going to matter. We're going to cancel it out anyway. Rate 2 is 150 molars per second. Rate 1 is 24 molars per second equals K 0.25 to the X 0.20 to the 1. K is 0.10 to the X and 0.20 to the 1. So now we do 150 divided by 24, and we get 6.25. Again, the units cancel. So this part is canceled out, the K is canceled out. So 0.25 divided by 0.10. We get 2.5 to the X. So when we go and resolve this, obviously X is not 1. So therefore X is equal to 2. And now we can write the rate law. Rate is equal to K, even though we can solve for K. Rate is equal to K times the concentration of nitrogen monoxide squared times the concentration of bromine to the 1. And I'm going to write the 1 in just for fun. So then we look at question B. It says calculate the average rate constant for the appearance of Nobr. So we're just going to take our rate law that we just solved and we're going to rearrange it for K. So we get K is equal to rate divided by the concentration of nitrogen monoxide squared, concentration of bromine, like that. So it says the average value of K. So I'm going to show the first one, and then we'll just sort of fast forward and look at what the average was. So we would do this for each experiment. So I'll take the data from experiment 1, the concentration of NO, the concentration of Br, and the rate, and I'll plug it in to this equation. So the rate is 24 molars per second. The concentration of nitrogen monoxide, concentration of bromine, and that gives me 1.20 times 10 to the 4, and the unit is molar to the negative 2, seconds to the negative 1, and that unit with K is typical of a third order rate law. So remember that the order of the rate, this would be second order with respect to nitrogen monoxide because of the 2, and first order with respect to bromine. Overall, we add the exponents and we get it third order. This rate law constant has units consistent of a third order reaction. You would do this and repeat this for each experiment. And when you do that, you'll actually find that the rate constant is the same each time. So the average is 1.2 times 10 to the 4. If a question asks you to do the average, you need to actually show that you've done all the steps. But normally it might tell you, just to save time, to calculate the rate law constant with respect to reaction 1. And then that's what we would have done. So Question C says, how is the rate of appearance of NOBr related to the rate of disappearance of Br2? So first, we're just going to write out the chemical equation. NO gas plus Br gas so we just write out the chemical equation. Now it's asking for how the appearance of NOBr is related to Br2. So we want those two. So there is a general form, and if you don't remember it, it's negative 1 over little a times the concentration of A, the concentration outside, so basically this is how we use the stoichiometric coefficients to calculate the rate laws and how they're related to each other. So what we do is we take the coefficient and we take the inverse of it and put it out front, and then we can actually talk about them directly. So we're asked about those two. So let's deal with NOBr and bromine. So bromine's coefficient is 1, so it will be negative 1 over 1 times the change in concentration of bromine over change in time is equal to positive 1 over 2 change in concentration of NOBr over change in time. So that's how they're related to each other. Now, we got to go back up and look at this equation. It says the following data is the initial rate of appearance of NOBr. So basically everything that we are doing is this part. Those rates are just the part that are inside those red brackets or parentheses. Everything else we have to rearrange and solve for. So what we get now is that the rate of disappearance of bromine is half the rate of appearance of NOBr. That's what we've written. Obviously, I don't need to write the 1 over 1. I do need to include the negative because it is a disappearance. But other than that, we are probably okay. So now for question D, we're just going to use this information. So for question D, we're going to plug in the values. So the rate of disappearance of bromine is what we're after. Now, it's giving us a concentration of NO and a concentration of Br2. So I'm just going to switch over to colors because we need to solve for something first. Let me use this little space up here. We need to actually solve for the rate with those concentrations. So I'm going to write out my rate law. And then we're just going to substitute the values in. So I know what K is. I got that above. 1.2 times 10 to the 4 molars to the negative 2, seconds to the negative 1. And I'm going to plug in the concentration part D gave me. So it said NO is 0.075 squared. That's molar. And 0.25 molar squared. So the rate, when I go to do it, is 0.075 squared times 0.25 naught squared times 1.2 exponent 4 equals 16.875 molar per second. So that's the rate, and that's in terms of Nobr. So now what I do is I simply go equals plus 1/2, and I'm going to plug in that rate for Nobr, 16.875 molar per second. So basically I just take the answer I got and multiply it by 0.5 and I get 8.4. As my answer for part D. So that's a pretty typical question with regards to kinetics. For question 2, we're going to look at something that's very similar. It's essentially the same idea, except it's a different reaction. It says, consider the reaction of peroxydisulfate ion, S2O8, -2, with the iodide ion. This is actually part of the reaction that we would have completed in lab. So it says, at a particular temperature, the rate of disappearance of S2O8 varies with reactant concentrations in the following manner. So once again, we get our table of data. It says, for letter A, it says, determine the rate law. So let's see if we can do this. Let's see if we can actually just rationalize our way through. So 0.027 divided by 0.018 is an increase of 1.5. So this is 1.5, and iodide's being kept the same. So now the trick is to have a look and see what the rate, how the rate increases. So I have 3.9 divided by 2.6. Again, you got to watch that the exponents are the same just to do the numbers there. And this increases by 1.5. So by increasing the concentration by 1.5, I'm going to increase the rate by 1.5. So that means the rate is first order with respect to S2O8 -2. Again, what we are doing here is we're just looking at the table and we're trying to save ourselves time, do it a little bit quicker as we gain confidence in this process. If you choose to use the X and Y method we used in question 1, that works as well. Now let's find one that's the same in another aspect. So in this particular experiment, they never held S2O8 to be constant. So that gives us a little bit of an issue. We do, however, have the data. We know that the rate law has power 2 for S2O8. So as far as we know right now, the rate is equal to K S2O8 -2 to the first power, and then iodide to the X. We don't know what X is. We have all of the data that we really need here. We should just be able to pick any particular 2. Again, because we do know that S2O8 is related to each other with 1. So I'm going to just simply pick reaction 3 and 2. So I'll put 3 on top. Just write it out again like we would have on the front page. Plug in the data for experiment 3. Experiment 2. K's are going to cancel out in this case, so I didn't have to worry about them. And now we're just going to put S208 in 0.036, 0.027. And again, they're both to the first power. And 0.054 to the x, 0.036 to the x. So 2 equals 0.036. Zero decimal 0.054. So we get 2 equals 1/3, 1.5 to the x. Multiply these together, 2 equals 1.95 to the x. Therefore, x must be equal to 1. Again, I know that it's not technically, but it's pretty close with regards to my rounding. So rate equals k, S208, -2, I minus, there's our rate law. For question B, it asks us to rearrange that rate law and solve for k. K equals rate over S208 over I. We pick any experiment. I'm just going to pick experiment number 1, and I'm going to substitute this data in. So 2.6 times 10 to the negative 6 molar per second, 0.018, 0.036, and this is molar, equals 4.0 times 10 to the negative 3, molar to the negative 1, seconds to the negative 1, as you would expect for a second order rate law. If you do this for each trial, you'll get the same number every time, so I'm going to save us time and just show us the one. Question C, how is the rate of disappearance of S208 related to the rate of disappearance of iodide? So I know I have 1 over 1 make sure we write out this equation, S208 -2, sort of separate this out, plus 3 iodide ions, 2 sulfate, plus I3 negative. So we have the equation. So we know that this is a rate of disappearance, so it's negative. It's a negative. Change in concentration of S208 over delta T is equal to -1 over 3. So the rate of this is equal to 1/3 of the rate of iodide disappearance, which makes sense because you need 3 times as much of it. So that is the answer to C, that part there. Just plugging in our coefficients. It says, what is the rate of disappearance of iodide when the concentration is given? to be 0.025 and 0.050. So once again, we will solve for the rate. Rate equals KS208 I minus rate is equal to the K that we found. Concentration of S208 from part D. Concentration of iodide for part D. Throw that through the calculator. Equals so 5 times 10 to the negative 6 would be the rate, and this is of course with respect to S208, and the question asks with respect to iodide. So I need to go back to my question here, take this and substitute it into this side, sorry. So it's to go into here. So 5 times 10 to the negative 6 molar per second equals 1/3 the rate of disappearance of iodide. To get that 1/3 over, I'm going to multiply both sides by 3. And that should be the rate of disappearance of iodide, or 1.5 times 10 to the negative 5 if you prefer. So now we get a chance to have a look at integrated rate laws and how they will affect, how we can use them to sort of affect solutions. So question 3 says, for a second order rate reaction, what quantity when graphed versus time will yield a straight line? So there are 2 particular integrated rate laws. For first order, if you graph on the y-axis the natural logarithm of the concentration of your reactant at a given time, and then we of course have slope, versus the time in seconds or in minutes, depending on what you're after, and depending on what your rate of reaction is, and of course the intercept is the ln of the original concentration. That's for first order. For the second order rate law, we have 1 over the concentration of A at a particular time and it's going to change a little bit on the other side. So instead of just K, negative K, it's K, T. So it's the same, it's just a slight change. And then the intercept is 1 over the concentration of A at the initial time. So for both of these, we have y equals mx plus b. We have y equals m, which is the K, x, which is T, and of course the intercept, which is not going to change. So for question A, you're going to have to graph 1 over A0 AT versus time. It's for A. For question B, it says, how do the half-lives for first order and second order rate laws differ? So the thing is with half-lives is a half-life is the amount of time it takes for half of the sample to react. So for a first order rate law, the half-life is equal to the natural logarithm of 2, which we solve out to 0.693, divided by the rate constant. That's for the first order. And for the second order rate law, we get half-life is equal to 1 divided by the constant. Notice the 0.693 is not there anymore, times the concentration that you initially started with. So question 4 says molecular iodine I2 dissociates into iodine atoms at 625 Kelvin with a first order rate constant of 0.271 seconds. What is the half-life for this reaction? So first of all, the units on the rate constant tell us that it's first order anyway. Even if it didn't tell us first order here, the units will tell us because inverse seconds is a first order rate law constant. So T1 half is equal to 0.693 over K equals 0.693 over 0.271 seconds to the negative 1 is 2.56 seconds. Now, for part B, it says if you start with 0.05 molar I2 at this temperature, how much will remain after 5.12 seconds? So there's a couple ways that you can do it. You can actually use the first order rate law, or you can actually plug it in and look and see that that's 2 half-lives and divide this in half twice. But we're going to actually just do it using the first order because it is a first order reaction. So we're going to use the integrated rate law. Because if it's not a perfect number, then you would probably want to know how to do that. So I want to know this particular form. I know what AO is, so my initial is 0.050. I know that my time is 5.12 seconds. I know that my rate constant is 0.271, and that's what I'm trying to solve. So now we're just going to plug along and get it. Ln A to T is equal to negative 0.271 seconds to the negative 1, 5.12 seconds, plus the natural logarithm of 0.050 molar. So 0.271 times 5.12 equals negative 1.38752. No units because the units will cancel out. And 0.05 natural logarithm 2.99573. Let's add those up. So I have the natural logarithm is equal to negative 4.83. So 4.383 negative. To get that out of the natural logarithm, I'm just going to put e to the x in. So the concentration of A at time t is equal to, I put that t inside, 0.0125 molar. which is exactly what you would get if you divide it by 2 twice, because 5.12 is exactly 2 half-lives. A lot more labor intensive, but if you were not given a perfect number, this would actually work as well. So from the following data for the first order gas isomerization of CH3NH, so basically just the N and the C are going to switch places, calculate the first order rate constant and half-life of the reaction. So again, it tells you first order. We're dealing with a gas, so it's going to be, instead of pressure, we're going to deal with the ln of the pressure. So for each one, 502, 6.219, 5.814, 5.193, 4.559, 3.731, 3.109. So what we're going to do is we're going to graph that. Now normally I use Excel, and I'm hoping to actually just go through how to do that right now. So what we'll have to do here is we're going to have a look at the various ways that we can do this on Excel. And the first thing we would do is just plug in the data. So we have temperature versus the pressure. So we're just going to go through and actually fill that out. So we fill in our pressures, which are in torr. So this is not just pressure. We're going to be using integrated rate laws to do this. So what we'll do is, instead of pressure, it's first order, which is what the question says. We're going to have to plot the natural logarithm of pressure. So that is ln p. So we're just going to click up. We'll put a title in that says LNP, so we remember what's in that column. And then as we need to do this for every single equation, we're going to start with the equal sign. And then we type the function that we're going to use, so ln, and then it starts to tell me what I need to do. So open bracket or open parentheses. And I'm going to select the cell to its left. So you can just go over and click on it. You can hold Control and click multiple if you had to. And then close the bracket. And it equals. So there we get our number. Now you could do this for each one, or you can actually just drag it. So if we drag it, it will do the calculations using the cell directly to its left. So it's all relative. So based on where the cell was, you could do it. There is ways within Excel to actually control or lock the cell that it's being used. So if you had a constant in this sheet, you could lock it that way by using the dollar symbol in front of the letter and the number in the cell you've selected, but that's not really helpful here. Just something to know. So we're going to go over and we're going to select the plot. It's just a scatter plot. It's going to open up a blank chart, and I'm going to go down to select data. Now it's going to open up this box, and I'm going to go down and add data. So it opens up this box and it asks for series name. And the series name that I'm using for this is just something that matters, integrated rate, put the chemical down. Now I'm going to select my X values, so you click on the button to the right, I go over, I select my X values, just drag them, and then hit the button to the right. I go down to the Y, delete that equals 1, click the button to the right, go over and get my ln P numbers. Hit equal, you can see the graph is populated. Just hit OK twice. You can click the chart layout, and you can pick different styles of chart. You can delete, you can easily add axes in this case, or the labels. The great thing about doing this is that you can copy and paste this right into a lab report if that is something that you had to do. So once you have that done, you're going to go Format Trendline. I'm just going to scroll down here on the right and select Show Equation and show R squared. R squared is how close the linear fit is. So 1 would be the maximum. You can see that that's what we have. So we have a perfect linear relationship, which would be pretty strange in an actual chemistry experiment. So there's my slope, and I can take that over and drop it right in. You can see it's 0.0002. We can get more precision if we want. So if we write equal slope, open bracket, you can say it says known y's. So I grab those, put a comma in, known x's, grab those, hit equals. You can see I'm getting a little bit more precision. If you need more than that, you can right click on this cell and go Format Cells. It'll take a minute here to load up. And go down and hit number, and then just increase the level of precision there. Hit OK, and you can see you can have as many digits, whether they're significant or not. That's fine. You can do the same thing with intercept. If you don't really need to graph it, you just need the values. So just write equal intercept. And then it's going to ask for known y's and known x's. Do the same thing we just did and hit equals. And you'll see that that is the concentration, or the natural logarithm of the concentration at time 0, which is right up there. And that's all we can do is Excel. Again, you can copy and paste this into a lab report. You can delete it. It's pretty useful to be able to do this. So what we get out of that is that we get that the slope is equal to negative 2.08 times 10 to the negative 4 seconds to the negative 1. It is first order. We know that k is equal to the negative slope. So k is equal to 2.08 times 10 to the 4 seconds to the negative 1. So again, you could use a TI. You could graph it by hand and try and get the slope that way as well. You should get a pretty close answer doing it by hand. The other part that this is asking is for half-life. So it is first order, so 0.693 over k equals 0.693 over 2.08 times 10 to the 4 seconds to the negative 1. And that's going to give me a half-life of 3. So this is to the negative 4. 3.33 times 10 to the 3 seconds. So negative 4. Those should both be negative 4s. That's simply how you would use integrated rate laws to do that particular type of problem. So on the last part here, it says, for an elementary process, N2O5 produces nitrogen dioxide and nitrogen trioxide. The activation energy, EA, and overall delta E are 154 kilojoules per mole and 136 kilojoules per mole. 136 kilojoules per mole, respectively. So 154 kilojoules per mole and 136 kilojoules per mole. So for question 6, it says, for the elementary process, given the activation energy EA and overall change in energy 154 kilojoules per mole and 130 kilojoules per mole, respectively. For A, sketch the energy profile. So we have energy on the side, and we have the progression of the reaction, or let's just use time on the x-axis. So first of all, the change in energy is positive 154. So from here to somewhere's up here, delta E is, 136 kilojoules per mole. The activation energy, this is not going to be to scale because I don't have enough room. The activation energy is going to be 154 all the way down, 154 kilojoules per mole. I'm used to doing the exothermic ones. So then you just take the profile and sketch it out. EA is the distance from the starting to the top, so it's the whole thing. And the delta E is the state function part of it, just between those particular lines. What is the activation energy for the reverse reaction? So if I was to go backwards, if I was going backwards on this, picture, rather than redraw it, picturing it going backwards this way, the activation energy would just be this part. And to figure out the difference between that, it would just be 154 kilojoules, take away 136 kilojoules, equals 18 kilojoules. So the reverse would be backwards. So you have to be careful. It's not just like enthalpy where you flip it backwards. You actually have to take a look because the profile will be completely flipped. So for question 7, we're going to use Arrhenius. And Arrhenius' equation was simply the natural log of the rate constants. So remember that rate constants are temperature dependent. So as you change the temperature of your experiment, you'll get different Ks. So if you were to start an experiment like we did in lab, where we did 4 different experiments, but we did it over 2 days with vastly different temperatures, we would be building in air that would just be based on the temperature. So you would really need to control your temperatures. But the natural logarithm of K is equal to negative EA over the gas law constant. This gas law constant is 8.314, 1 over T plus the ln of the frequency factor. So just so we're clear, we have Y equals M X plus B. So we have a linear equation. So we can't just graph, we cannot just graph ln versus K. We actually have to graph it a little bit different. We have to actually change these variables so they match our equation. So for example, our Y variable is not just K, it's the natural logarithm of K. So ln K. And what we can do is basically take the natural logarithm of each. Now I'm just going to create a separate table, negative 3.57, negative 1.51, 0.262, 1.79, and 3.13. With the temperature, we have to do the same thing. We have to actually take the inverse of the temperature. So 1.67 times 10 to the negative 3. These are all going to be 10 to the negative 3. 1.54, 1.43, 1.33, 1.25. Again, times 10 to the negative 3. So basically, if we plot this as our x, remember this is our x, and we plot this as our y, we will create an equation. Excel is great at doing this and doing it quickly. So when you use Excel or your calculator, you'll get an equation that says y equals negative 16,108x plus 23.271 as your intercept. Now we know that the slope of the line is equal to the negative EA. So negative 16,108 is equal to negative EA over R. So remember that R is not the one we used during most of the gas laws. It's 8.314. So EA is equal to negative 16,108 times negative 8.314. We're just going to take that negative over. So the activation energy in this case is 16,108 times 8.314 is equal to 133,900 and let's call it 22 joules per mole. The activation energy is equal to 133.9 kilojoules per mole. So that's the activation energy. Second of all, it asks us to find A, and that is the intercept. So I know the natural logarithm of the frequency factor is equal to 23.271. So A is equal to e to the 23.71. A is equal to, so 23.271 is equal to 1.278 times 10 to the 10. And if you need help or you want to use Excel to do these types of questions, as you can see, it's pretty easy. Then make sure you check back in or you come in and see me and we'll be able to sort that out, or figure out how to use it on your calculator. That would also be something that would be very useful for you.